In section 4 of chapter 4, we're going to be kind of tying this stuff together. It's more of an extension from section 2. We took a brief pause to go over the square root method, the algebraic process. This is more of a continuation of section 2 where we're going to be solving quadratics. In section 2, I gave you problems that were mostly factored. This is where we're getting to the traditional problems, which are, hey, here are a bunch of quadratic equations. Solve them. You have a bunch of different factoring techniques at your disposal. You have the area model. You have difference of squares, perfect squares. You have GCF. Those are usually enough to get you through most of them. There are other factoring techniques like the diamond method. There's a tick-tock method. There are reverse area model methods. There's a bunch of different techniques that you can use to solve quadratics. Again, I'm going to ask that for right now we stick with the area model purely because the lesson we're going to do after this, if you know and have used the area model regularly, it is super easy. If you are not familiar with the area model, it becomes one of the most difficult concepts in Algebra 2 to do. So that's the main reason I teach the area model is for the lesson after this one. All right, so problem number 1. I want to solve that equation. I want to solve for x. I want to find the x-intercepts. I want to find the roots. That means that the y value is 0. The reason that's important is because factoring only works if the equation is equal to 0. If it's equal to anything else other than 0, you cannot do it. Additionally, I'm actually going to move these equations around just a little bit so I have more space. So I realize these are kind of vertically intensive. So problem number 1, I have x squared plus 8x plus 15. I want to factor that. There's no GCF because they don't all three have a term in common. Means I have to use the area model because it's not a difference of squares, it's not a perfect square trinomial. So I just got to use my tried and true area model. These two terms have to combine together through addition to get me that positive 8x. Therefore, I need an x times x. Numbers that multiply to 15 are 1 times 15, and then 3 times 5. If we use the 3 and the 5, you'll get a 3x and a 5x. Those will add together to get the 8x in the middle as long as they're both positive, which means I need a positive 5 and a positive 3. I'm speed running my way through this factoring problem because this should be familiar to you. The focus should not be on factoring. The focus should be on the next step, which is when you get 0 is equal to x plus 3 times x plus 5, going from that to the solution. I would set each one of these equal to 0. I would solve each one, subtract 3, x equals negative 3. Subtract 5, x is equal to negative 5. These are my two solutions. So again, I got a quadratic, it was equal to y. I set y equal to 0 because to solve for x-intercepts, the y value is always 0. I factored using an area model because there was no special technique to solve this. Once I factored it and I got the product of two binomials is equal to 0, I set each of the binomials equal to 0 and solved, and those were my solutions. Once you do enough factoring problems, they become incredibly repetitive. It's the same process. It's just the numbers change, which makes the area model sometimes more or less difficult. Problem number 2. I set the y value equal to 0, which is the same thing as basically just scratching it out in this problem. I can only factor if it's equal to 0. It's not equal to 0. So what I'm going to do is I'm going to add the 6x squared to the other side for two reasons. One, I want it equal to 0, and now it's equal to 0. And two, the reason I didn't move the negative 11x and the negative 7 on the right to the left side is I like it when the x squared term is positive. It makes the factoring steps a lot easier. All right, got to use the area model. This one's a little bit more difficult because the leading term in front of the x squared is non-prime. It's a 6. That means I can get it by doing 1 times 6 or 2 times 3. 7, luckily, is prime, so it's just 1 times 7. I have to run through all the iterations in my head until I find one that generates an area model where these two boxes have a difference of 11. I'm going to cheat because I already know what the answer is, because I made the problem. It's a 2x and a 3x. I'm going to put a 1 here and a 7 here, because that'll give me a 14x and a 3x. Those two can combine through subtraction. Those two can combine to get a negative 11x as long as the 14x is negative and the 3x is positive. Meaning the 1 needed to be positive and the 7 needed to be negative. So again, I went through that really, really quickly just because, again, I have the key already. So this factors into 0 equals 2x plus 1 times 3x minus 7. Once you become well versed in this, you can kind of skip this step and do this in your head. If I set 2x plus 1 equal to 0, I'd have to subtract the 1 to the other side and then divide by 2. That means I'm going to have x is equal to negative 1 over 2. If I had 3x minus 7 equal to 0, I'd have to add the 7 to the other side and then divide by 3. So that would become 7 over 3. And those are my solutions. Problem 3 is the tricky one of the bunch. Doesn't look tricky when you first start it, but I'm going to add the 2x to the other side, and that would give me 0 equals 2x squared plus 3x plus 5. We construct an area model. It looks really easy because we have a 2x squared here and we have a 5 here, and these two have to combine to get me a 3x. It seems really easy because the 2 is prime and the 5 is prime. So let's put the 2x here and the x here. If I put the 5 here and the 1 here, I'll get a 5x and a 2x. Those would add together to get me 7, not the 3. All right, so that doesn't work. The 1 and 5 in that orientation don't work together. So let's try swapping them up. Let's try putting the 5 here and the 1 here. That gives me a 1x and a 10x. Those don't add together to get me 3. Did I make a mistake? Did I type it out wrong? Did I forget a negative? Oh no, whatever shall I do? What you should do if an area model is giving you a pain is use the discriminant. Maybe it's not factorable. This discriminant will tell me. If the discriminant is negative, definitely not factorable. If the discriminant is positive but not a perfect square, it's not factorable. So let's do the discriminant. B squared minus 4ac. So that would be 3 squared minus 4 times my a value is going to be 2. I accidentally deleted it. Times c, which is 5. That means 9 minus 40. It's negative 31. That means we have two complex solutions, two imaginary solutions. But for us, that means it's not factorable. But in this case, it means no real solutions.